Hello, everybody. Welcome back to another discussion dynamics. Today we'll start a new topic. Namely, we'll start kinetics of rigid bodies. If you would like to place our topic on the timeline, it's here. And today we'll just do a brief lecture review and then 3 examples. So without further ado, let's dive straight into our discussion. Let's start with a brief lecture review. So what do we have in here? So right now we have a rigid body. And for the first time this semester during our discussion, yes, we consider that body as an object that has mass, yes, and moment of inertia about point C, so-called center of mass, yes. So if you recall all the discussions we run in this topic, in kinematics of rigid bodies, have we talked about mass in there? No, mass does not appear. Did not appear in any of the problems, yes? We only cared about geometry of the body, yeah? So right now, for the first time in discussions, we're gonna consider mass and moment of inertia of the body. So let's assume that our body is subjected to some force, some net force F, and also that some moment here rotates our body. So it will result in acceleration and also some angular acceleration. And if you would like to put this free body diagram and kinetic diagram in a mathematical form called equations of motion, here they are. So sum of forces acting on the body will result in inertia experienced by center of mass. Okay, so it's MAC, it's no other point, it must be point C. And if you would like to sum the moments acting about point C again, it will result in IC times alpha body. So the only thing you should remember here is that we look at center of mass, no other point, okay? At least today. That's it. Any questions? Yeah. That was the lecture review, yeah? Probably from before the Thanksgiving, yeah? Okay, I don't see any questions. So let's do example number 1. And as usual, please familiarize yourself with the problem statement before we start our solution. However, the requirement I told you at the beginning of the semester that you should familiarize yourself with the problem statements before coming to these discussions is still valid. So I assume that all of you read it, yes? So let's dive straight into our solution. What do we have in here? We have our beam, which is uniform cylinder rod, and we know its mass, we know its length, M and L respectively, and since it's uniform and cylinder rod, we know that cross section is constant and also density is constant. And they ask us to find moment of inertia about this axis Z, and also radius of gyration about that Z, about the same axis. Okay, and we're just going to use the definition for IZ and KZ. Any questions about the problem statement? Great. So let's just follow the definition. Yes, I'm just going to start our derivation with the definition. So this is definition for IZ. Maybe let me tell you what is this dm and r. So this dm is already in the picture, yes, but I can draw it one more time. Yeah. So this is our dm. This is infinitesimal mass. And what is r? R is obviously the distance between axis r and the dm. And our dm has length of dr. Oh, sorry. Okay. So what can we do in here? I think that mass of that infinitesimal mass can be expressed as rho times dv, where dv is naturally infinitesimal volume. So the integral of rho r squared dv, and this is volume. Yes. Moreover, our dv can be expressed as a dr, right? So that will be rho a r squared dr, and this integral will be over the length. Okay, so I believe that they told us that this is constant, yes? Rho and a is constant. So we can put it in front of our integral, yes? So we can actually write integral, oh, sorry, rho a integral of r squared dr. And maybe some of you can tell me what integration bounds I should put in here based on the picture, this picture. Anybody wanna say something? If not, it's fine. Oh, it will be from minus L half to L half, yes? Yeah, this is where our z is located. So in here I will just put minus L half to L half. And I think I even know how to solve that integral. So this is rho a 1/3 r cubed from these integration bounds. And if I plug them in, we'll end up with something like that. 1/3 L half cubed minus L half cubed. Yeah, if you solve that, you will end up with 1/12 rho a L cubed. Okay, and now let's go backwards, yes? Because I think that our volume of the entire beam can be expressed as A times L. So I can continue our expression with something like that. To be 1/12 rho V L squared. Moreover, the mass of the entire beam is rho V. So it will be 1/12 ml squared. Great, and we are done. Iz of our beam is 1/12 ml squared. This is the answer to part A. Yeah, so I know that you knew it probably in statics. Yes, maybe even some of you knew it in high school. So in case you were wondering where that 1/12 ml squared comes from, it comes from here. Any questions? We good? Cool. So second part of the problem is to find Kz. So we are just going to use this definition for Kz, and we are just going to equate the right-hand sides of these two expressions. This one with this one. All right. I mean, all right. So let's do 1/12 ml squared is equal to mkz squared. M cancels out, and we end up with kz equal to square root of 12 divided by 12 L. Okay, so this is answer to part A, and this is answer to part B. Any questions? Okay, so what? Do you want to do example number 2 right now? Let's do it. Example number 2. As usually, please read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have a cabinet, and we know that it has weight of 230 pounds. There is some guy pushing it, yeah? So we can model that guy as a force P applied at this point. We're gonna do it in our solution. Moreover, we know that there is a slip between the cabinet and the ground, and coefficient of friction is 0.28. And we know the entire geometry of the cabinet. Okay, and they ask us to find H. So this H, the point of application of that force P, so that the cabinet does not tip over. And actually, they ask us to find the maximum height of that force P. Yeah? So basically, if that force P is applied a little bit higher than H, then the structure will start tipping over. Okay. And then they ask us to find acceleration of point C. Yeah. One digression, I usually call center of mass C. Usually, I think even everybody else in the discourse, they call it G. Okay, so just, I don't know, get used to it. Okay, I call it center of mass C. Many people call it G. But we both mean center of mass. Okay. Any questions about the problem? You never have questions about the problem. Yeah, I probably should stop asking that question, yes? So to solve that problem, we will follow the recipe I gave you a couple of weeks ago, yes? So this is kinetics of rigid bodies. So I'm not sure if you remember the recipe, but the first part of it was FBD and KD. So in here, I will just model that cabinet as a rectangle with center of mass located here. Okay, and I'm going to copy it to our KD. Oh, that's interesting. Why did you do that? Oh, interesting. Okay. So now the question is, what forces act on our system? So I'm gonna go for the easy ones, as usual. So I think that there is mg acting here, and I also think that there is that force P, yeah, that pushes our body. What were the dimensions? That was h, I believe, and that was, I forgot, d. Let me scrub the board. Yeah. Okay. And now I don't know what to do. So maybe some of you will tell me, are there any other forces acting on our system? Sam. Friction, exactly, yeah. So where I should apply it? At the base. Okay. We are getting closer to our solution, yes. So do you want to apply it at the base, but at this point? At this point? Or at this point? Yeah. Think about it.
I'm thinking the second one, but
the second one, which one? In the middle, here. And why do you think so? No worries, no worries. We have somebody else. Wait a second. Anybody else? Yeah. So let's go for Ian. Okay. You mean here?
Yeah.
And you said that this point has no forces.
No, it's not the point on the left side.
Yeah. And why? Okay, so this is correct answer actually, Sam. Yeah. So why? Yeah. So why did you choose that point?
Yeah, so at the moment that it starts ticking, the point on the left side is on the left side.
Exactly. Perfect. This is the yeah. So this is what you want to say? This is what you wanted to say? Yeah. Doesn't matter.
I'll say yes.
Yeah. So anyway, Ian is right, because this is point of contact right before our object starts tipping over. Yes. So this is point of contact right before cabinet starts tipping over. Great. So we have basically normal force acting here. So it will be N. And also we have friction acting this way at this point. Yes? Okay, we are done with forces. And now let's just do our routine on kinetic diagram, okay? So in here, I'm just gonna put MACX, MACY, and let's assume positive direction of rotation, okay? IC alpha body. All right. However, I think that we can say something more about, for example, ACY. What is the value of ACY, guys? Anybody wanna tell me? 0, exactly. Because the trajectory, the trajectory of point C is this. And this is the trajectory of point C. So point C must follow the horizontal line, yes? It cannot leave that plane. It must be 0. And by the way, we don't want our body to tip over, yes? We don't want our body to rotate. So I'm not gonna even ask you. This is also 0. Yeah, our body is not rotating. Okay, Drew, do you have a question? No worries. Yeah. Okay, anything else? I think we are done with FBD and KD. Any questions? So I hope that you remember the second step in our recipe. Second step was in equations of motion. So we are just going to write sum of forces in the x direction with this direction as positive, sum of forces in y direction with this direction as positive, and sum of moments about none other than point C. Yeah, we can always do that. We can always write sum of moments about point C. So what forces act in the x direction? Only two, P minus TF. And this is equal to MACX. Now, y direction. So we have minus mg plus n, and this is equal to MACY. Yeah. And you guys told me that this is 0. So this is 0. And we just found what is the normal force. So that means that n is equal to mg. Okay. And the third equation, we have some forces rotating about C. For example, P. And P rotates in a negative fashion, right? Right, yeah. So it will be minus P times this distance, h minus d. Now, let's say TF, friction. Friction rotates again in a negative fashion. So it will be minus TF d. And N rotates in a positive fashion. So it's plus N. And what was that distance? Let me scrub the board. Was it the W? Yeah, it's a W. Yeah, okay, so I'm gonna put it here. So this is W. So in here, I will just put W over 2, yeah? And this is equal to IC alpha body. And since this is 0, this equation will be 0. Awesome. Next step in our recipe, I hope that you remember, was counting number of equations and number of unknowns. So let's see what do we have in here. We have one equation. We have second equation here. Uh-oh. And let's see how many unknowns do we have. Aha, we don't know this guy. I am afraid we don't know friction. And I think that the point of that problem is to find h, yeah, the point of application of point P. Okay. Okay, so unfortunately we have 2 equations and 3 unknowns, but we will solve it soon. Yeah, so we have 2 equations and 3 unknowns. However, they told us that friction is in kinetic region. Yes, So we can write kinetic regional friction, kinetic friction, and Tf is equal to n times mu k. So this is equal to mg mu k, because we found n like 5 minutes ago, yeah? Okay, and all of a sudden our system of equations is solved, yes? So we have P minus mu k mg is equal to macx, and in here we'll have, I'll just copy it, okay? Just copy that equation, and I will replace Tf with what we just found. Okay, so it's mu k mg. Okay, so we have 2 equations and 2 unknowns. Solvable. Okay, so if you solve it, you will end up with ACX equal to 1 over m P minus mg mu k. So let's plug in values. So in here we will have 1 over 230 divided by 32.2. Yeah, please remember, so our weight, our cabinet weighs 230 pounds, yes? So please do not forget to divide that by 32.2, okay? And in here, I think that P was 70 minus 230, mu K was 0.28. Yeah, if you grab your calculator, you will end up with ACX equal to approximately 0.784 feet per second square. Yeah, and we obtained positive value, so that means that our ACX vector is equal to 0.78400 feet per second square. Yeah, which is physical, yeah, because that guy is pushing it towards the right. Our cabinet has to go towards the right. And this is actually not what they ask us for. They ask us to find h. So h can be found from this expression. And if you solve it and plug in values and grab your calculator, you will end up with h being approximately 2.21357 feet. Cool. So these are the answers. Ah, yeah. So actually ACX, oh, sorry, not ACX, AC, yes. I have to get rid of this subscript, yes, AC. Ah, so actually AC was, they asked us for AC in the second part, yes. Ah, yeah. I forgot about it. Okay. So that's it. Any questions? So far, so good? Yeah. Am I doing good job so far with explaining that? Okay, good. Thanks, guys. Yeah, so before we start example number 3, you can think about questions. I want to say something. Yeah. So actually, the kinetics of rigid bodies is not much different than kinetics of particles. Don't you think? Because actually, we just, the problem boils down to this point. Yeah, to this particle. Yeah, do you see that? So, in other words, it doesn't matter what is the shape of our body. Yeah, would the solution to that problem changed if we have a different shape of the body, however, same mass, same moment of inertia, and same location of point C? It would be exactly the same solution. Think about it, okay? It also it's very helpful when you work for industry and you design stuff. So the shape of the body does not actually matter. It does not impact on the motion, yes? However, yeah, you just must make sure that it has the same mass, same location of center of mass, and same IC of the body. Yes, Vincent?
Oh, I was just going to ask that if what you meant by the same center of mass, that all the distances to the forces are the same.
Yeah, so all the distances from that point. Should be the same. Yes. As usually, yeah. From this point, yes. Okay. Any questions? And you are Jared. No, Jaden.
Can you explain why we put the normal force at the point of where you applied friction instead of in the middle?
Sure, because they told us that in this situation, our thing will start tipping over. Yeah. So it starts tipping over. Yeah. So that means that right before it starts tipping, the contact point between the object and ground is here. Yes. So before it is distributed. Yes. Before it is distributed along this direction. Yes. There are like some little forces acting here. Yes. But right before it starts tipping over, I'm going to repeat what I said earlier. Yeah. The contact point will be here. Yes. Yeah. Sorry, that was individual teaching. Do you understand, guys? Let me know. Yeah. This is exactly what I wrote in here. Yeah. Point of contact right before the body starts tipping over. Example number 3. Let's do it. As usually, please read and understand the problem statement before we start our solution. Okay, so what do we have in here? We have our rod being placed on the table. Yes, so basically, if you think of that pen, I just put it on the table, yes, and this is the rod, yeah. So gravity acts into the board, yeah, gravity acts into the board. So we have our beam that is placed on the table. We know that it has mass and length and IC of following values. Oh, by the way, it's 112 ml squared, so exactly what we found in example number 1. And then we also have some force P applied to that beam, yes? And the distance between point C and that force is h. We know that system starts from rest, which is always good. By the way, every time you see that system starts from rest, you can set up every single velocity to 0. Yeah, which is good. You will see why it simplifies the problem in a second. And by the way, there is no friction between the table and our beam. They ask us, again, for point of application. Okay, so they ask us again, where to apply that force P such that this acceleration is 0. Okay. And then once we solve part 1, they ask us to find acceleration of this point A. Okay. So we're just gonna follow the recipe. I'm gonna draw a free body diagram and kinetic diagram. So this is our beam. I'm gonna put center of mass in here. So this is C. I can draw nicer C. Okay, and I'm just gonna copy that to our kinetic diagram. Okay, so we have mg acting in this direction. And there is like a normal force distribution that prevents that body to penetrate the table, yes? So we can just ignore what happens in the direction perpendicular to the board. So I don't know, I'm just gonna, instead of writing normal force, because I don't know where it is applied actually, so I'm just gonna write here normal force distribution balances out mg, okay? Normal force distribution balances out mg. Okay. But anyway, or you can equally write nothing interesting happens in the direction perpendicular to the board. Yeah, we ignore that motion. Okay, what other forces act on our system? Force P. And this is the distance h, I believe. Okay, there are no other forces acting on our system. So now let's just do our routine on the KD. So we have here MACX, MACY, and let's assume this direction. IC alpha body. Alrighty, we're done with FBD and KD. Next step, EOM. So we have sum of forces in the X direction, sum of forces in the Y direction, and sum of moments rotating about point C. So what do we have along the X direction? Just one force, yeah? So just P. And this is equal to MACX. Okay, how about Y direction? Nothing, 0. So it's MACY. Oh, great. So we know that ACY is 0. Great. How about moments? We have P rotating counterclockwise, no, clockwise. So it would be minus PH, and this is equal to IC alpha body. Great. We are done with EOM. Questions so far? Okay, so we're gonna follow our recipe. Now let's count our equations and unknowns. This, we have that. Okay, I already said that it's not good. So we have this unknown. So MACX is not known. I bet that this thing is not known. And I also think that they ask us to find H, yes? So we unfortunately have 2 equations and 3 unknowns. I don't know what to do. So maybe one of you can help me. How to find third equation? Anybody? I have time. No. Okay, because I again forgot your name. Don't say it. Jada.
Yeah.
Sorry.
Angular relation using circular motion.
Okay. Acceleration analysis. You meant. Yes, you meant.
Traveling in a circular, like if the time's traveling in a circular path.
I am not sure if it's a circular path, but it probably is. Yeah, because this guy is 0. Yeah. So at least at this time instant. At least at this time instant, yes. Okay. So anyway, what I just like to know. So look, the previous chapter of the dynamics course, it was kinematics of rigid bodies, yes? And we run the acceleration analysis, yes? Yeah, so let's go for that. Acceleration analysis, yeah, thank you. I again forgot. Analysis. So let's do acceleration analysis between maybe points C and B, because they told us that acceleration of point B is 0. So IC is equal to AB plus alpha body times RCB minus omega body squared RCB. So now you guys can see that the information about system starting from rest is useful because this is 0. System starts from rest. Moreover, they told us that this point is 0. The acceleration of this point is 0. So we can write here ACX, ACY 0 is equal to 0, 0, 0 plus 0, 0 alpha body times this vector. Okay, let's put it on the board. RCB. RCB will be here. This is point B. So you all guys can see that this vector is 0, L over 2, 0. Okay. So we can put it here. And we must do this determinant. Before doing the determinant, I actually want to tell you guys that actually we found this value, right? This was 0. We found it, yeah? So I can put 0 here. Oh, sorry. 0. And if you do this determinant, you will end up with minus alpha body L half 0, 0. So we can write minus alpha body L half 0, 0. Great. And our ACX can be found from via looking at the x component of this equation, this vector equation. So our ACX is basically minus alpha body L half. And thanks to Jaden, thanks to Jaden, we found third equation we were looking for. Okay. I'm not joking, actually. I'm sorry, man. I keep forgetting. Sorry. Maybe you can think of changing. Think of changing the name. Okay. Okay, so all of a sudden we have 3 equations and 3 unknowns. And I have no doubts that you guys know how to solve it, yes? So if you solve it, you will just end up with following values. ACX, alpha body, and H, which are respectively P over M minus 2P ml and L divided by 6. Okay, let's focus on this thing for a second. So we obtained ACX positive, yes, so that means that our AC vector-wise will be P divided by M 0, 0, which makes sense because our force pushes towards the right, so our AC also must go towards the right. And our force rotates clockwise, so it's great that we obtained negative value here. So this is minus 2P ml 0, 0. This is clockwise. Okay. However, in part A, they ask us, these are like byproducts, not subproducts. Sorry, guys. So these are like byproducts of our solution, yes? Because what in fact they ask us to find is this, yeah? So our answer to part A is H equals to, L divided by 6. Any questions to what happened on the board? Yeah. Kevin? Yes. Oh, shoot. Of course. Thank you. Thank you for paying attention. Thank you. Yes. Okay. Any other question? So let's do very quickly part number B. Okay. So part B. Let me scroll up the board just to see what they ask us for. Aha, they ask us to find acceleration of this body, of this point A, once we solve the part A. Yeah, so how to find that acceleration? Anybody? I can ask you to repeat.
Acceleration analysis.
Exactly, yes. Acceleration analysis, exactly. Between, I don't know, point A and C, or point A and B, whichever you want. So let's say A and B, it's faster. So we have AA is equal to AB, which is 0, plus alpha body times RAB minus omega body squared RAB. Okay, system starts on rest still, so this is 0. This is 0 because they told us. So in here we just have AA equal to 0, 0 minus 2p ml times this vector, RAB. Okay, and this vector is here. It starts at B and it ends up at A. And all of you see that this is 0, L0. Okay. So let's do it quickly and we can go home. Or wherever you want to go, L0. So if you run this determinant, you will end up with such expression, 2p over m, 0, 0. This is answer to part B. Any questions to what happened today? Any questions about what happened today? If not, I can just say one thing. Have a nice afternoon. Bye-bye.